Okay, class, let's see, this is the 14th. Working in chapter 10 still, and we are moving on and discussing microwave amplifier design. So you need to make sure you read those sections. Read all the way out to the end of the text. Okay. And where to begin? So, right, pretty interesting section. Right, well, with the amplifier, right, what do you need an amplifier for? Well, obviously, as the signal comes in from the antenna, right, it's weak, and so it needs to be amplified. Right? So typically, one of the very first elements in the receiver chain is a low noise amplifier. Right? So certainly part of the design is to determine the desired gain, right? And the gain is just going to be 10 log of the output power over the input power. And then another specification, common specification for the amplifier is the dynamic range, right? And that's typically specified in terms of the 1 dB compression point. All right, well, what's that about? Well, according to this figure, right, here comes the input power, and so the output power is, linearly proportional to the input power over some range of input powers. So at some point, the input power will saturate the amplifier, and that begins to happen right about here. And so the gain is really specified where there's this 1 dB compression, or the actual gain is 1 dB down from what it would be if the gain were linear over all ranges of input. Right? So the gain of the amplifier is specified at the 1 dB compression point. So remember what this is about. It's pretty simple, right? If you have a gain G and you have some input voltage V and some output voltage V in and some output voltage V out, then right, the output will be the voltage gain times the input over some ranges of input voltage, right? At some point, the output voltage is going to equal the power supply voltage, and then at that point, the output voltage can't get any higher than that, right? And so, for any input that forces the output to be equal to the power supply voltage, then any other higher value of input voltage is just going to cause saturation. So you've probably seen that in your lab work. So that's the same phenomenon as this compression. Okay, so right, you specify the dynamic range, the 1 dB compression point, you specify the gain of the amplifier, right? And then also the noise figure. Well, what's the noise figure about? Well, right, there is some given input noise coming off of the antenna, right? So the first stage of amplification, the low noise amplifier, has some amount of input noise that's going to be amplified by the amplifier. And so the output noise is going to be, right, the input noise times the gain of the amplifier. But and that would be the case if the amplifier were perfect, right? It turns out that it's going to add some more noise, right, to it, because it's not a perfect device from a noise standpoint. And so that noise figure, right, tells us how much additional noise the amplifier adds to the input noise, and that gives us the total output noise. Right? So a real good, expensive RF amplifier would have a low noise figure, meaning that it doesn't contribute much to the increase in noise through the amplifier. And then, of course, right, there's the voltage standing wave ratio at the input and output ports of the amplifier, right? So in this first little, right, read the text too. Now, Stu has a good discussion of this, so you need to read that pretty carefully. but here's a BJT, right? And so we're just going to build a RF amplifier with this, right? So it has uh, an input on this side and an output over here. And so you have an input coupling capacitor and an output coupling capacitor, right? R1 and R2 are just bias resistors, right? These are adjusted so that the amplifier is biased at some point. And then note here, right, you've got the emitter resistance that's bypassed via this capacitor, right? So the emitter resistance, as far as the AC circuit is concerned, this is a short to ground, like this bypass capacitor. So note these RF chokes in here as well, right? They have the ability to isolate the transistor from the power supply input, right? Because right, this is an inductor, so its impedance is J omega L. So at high frequencies, this becomes a block, right? And so the RF is forced into the transistor. It can't go up here to the power supply, which is a low impedance to ground, and short out. So you've got to have these RF chokes in here for this thing to work. Okay, so the output is typically larger than input because this is a common emitter amp. Okay, so if all the RF chokes are placed in here as required and the biasing is done properly, then from an AC standpoint, right, from a sinusoidal steady state standpoint, the amplifier can just be represented this way. Okay? So then it becomes S parameter representation of the microwave amplifier, right? Here's our input port, here's our output port, and so this is a two-terminal device, and so it's from a microwave standpoint, we're going to represent that with a scattering matrix, a 2x2 scattering matrix, S11 reflection coefficient here, S22 reflection coefficient looking back into the output, S21, right? Subscript, remember how the subscripts go. 2-1 is input on 1, output on 2. That'll be the forward gain essentially of the amplifier. And then S12, right? Input at 2, output at 1. For most for most of for most cases that'll be 0, right? There's no backward gain of the amplifier, and that's what we call a unitary assumption. Okay, so how is this thing used how is the RF amplifier used in the circuit, right? So here's a microwave amplifier. Here's our source. See it. This is the source, right? It has some source voltage and its internal impedance, Z naught, typically 50 ohms, a source matching network. Then here's our transistor. That's right here. And then the load matching network, and then the load. Okay. So note here that looking into the source matching network is gamma sub S. Looking into the transistors, gamma N, right, or S11. Looking into the output of the transistors, gamma out or S22, and then looking into the load matching network, gamma load, right? So this thing is going to operate optimally when the source, right, the source impedance, the source reflection coefficient is the conjugate of gamma in, and the load, looking into the load matching network, is the conjugate of gamma out, right? So in our designs, that's going to be really what we're shooting for. So our objective here is to learn how to design these source matching network and load matching networks, right? And so our intent then, right, is to adjust or create the either stubs or lumped elements, whatever we decide to use, right? And that's going to depend on the frequency of operation. If we're at high frequencies, right, 10 gig and above or several gig and above, we're going to need to use stubs here at the lower microwave frequencies around a gig or so, we can still use lumped elements for the source matching and load matching networks. Right. So how are we going to design these? Well, we need to translate the Z naught, right, which is at the center of the Smith chart. We need to design the source matching network in such a way so that looking into it, right, we have a reflection coefficient that's the conjugate of what we see looking into the transistor, because then that'll give maximum power transfer to the amplifier. And similarly here, right, we need to design the load matching network so that looking into the load matching network, starting at the origin, Z naught of the Smith chart, that is, we can eventually make this matching network give us an input load reflection coefficient that's the conjugate of the impedance of the reflection coefficient looking into the transistor. So that's how you design these things. All right, that said, right, let's move to page 2 and look at this. So we kind of fast forwarded a little bit on the design here. Let's kind of back up a little bit and see where that comes from. So, right, according to the microwave theory, right, which is pretty much stated in the text without proof, but here's your input reflection coefficient looking into the transistor, right? That's gamma n. That's right here. Go back to this. Gamma n. Whoop, I'll get it. Gamma n is looking into the transistor. So gamma n is right S11. That makes sense, but it also depends on the load reflection coefficient and S12 and S21 and S22, right? So every scattering parameter in general, every scattering parameter of the transistor, as well as the load reflection coefficient, what you see looking in the load, contributes to the input reflection coefficient. Similarly, the output reflection coefficient depends on every scattering parameter of the microwave network, as well as the source, what you see looking into the source of the reflection coefficient looking into the source matching network, right? Okay, so again, right, the gain is the power delivered to the load divided by the maximum power available from the source, right? So this is the available power. How do you compute that? We've been doing that with the we discussed that when we talked about filters, right? The available power is the power delivered to a load that has the conjugate impedance of the source impedance. So if your source impedance is real and 50 ohms, and it's just the amount of power absorbed by a 50 ohm load. So that's pretty simple. Okay, and then obviously we're going to want to express that in dB typically, which is just 10 log of the gain. And so, right, the gain is then represented this way, okay, due to microwave theory, right? So it depends on, if you look at this, note it depends in the middle here on S21. That makes sense, right? That's the S21 is the scattering parameter from the input of the transistor to the output. And so the power gain is going to be proportional to the magnitude of that squared. But you have these other terms as well, right? Because the source matching and what you see, reflection coefficient, looking into the source matching network and looking into the transistor and looking into the load matching network and looking into the output port of the transistor are all going to affect the gain, right? But if we assume, right, that if we assume that S 1, 2, right, in at 2, out at 1 is 0, right there, that's what we call a unilateral assumption. meaning that the transistor doesn't have any gain in the backward direction, right? And so that's a reasonable assumption, referred to as the unilateral assumption. Under those circumstances, then gamma in is going to be just S11, and gamma out is going to be S22, right? Because if you come up here and you replace S12 with 0, uh, that that sends this entire term to 0, this entire term to 0, then gamma in is S11 and gamma out is S22. So it simplifies, right? And under those circumstances, right, this simplifies as well. And so your gain under the unilateral assumption, which is the maximum gain of achievable, is still the S21, right, the forward gain of the transistor. And then, but it's got these other terms, 1 over 1 minus S11 squared, 1 over 1 minus S22 squared, right? Right, so for example, then, suppose you have, and this is example 1018, suppose you have a microwave amplifier and at the frequency that you're going to use it at, the S parameters for your transistor have been measured and they're given to you here. So you see immediately that S12 is 0. And so remember how this goes. Uh, output, uh, input, output, right? So output at port 1, signal input at port 2 is 0. So the backward gain is 0, right? And so that satisfies the unilateral assumption. And so if you find the gain without the matching network, it's just going to be magnitude of S21 squared, right? And so that since that's given as 2.2, that's going to be 2.2 squared or 4.84 or about 7 dB, 6.85 dB. But if you go to the effort, right, of that sneeze, if you go to the effort to build the matching networks, right, that's going to improve your gain, right? If you make uh, the source matching network have an input reflection coefficient, the conjugate of that looking into the transistor, and the load matching network, uh, input of the load matching network, the conjugate of the reflection coefficient looking in the transistor, then your gain is represented this way. And if you write that out, right, you're going to get 12, right? So it's S21 squared, uh, all right, but it has a multiplicative factor here and here. So these are helping your gain. So here you get 12 uh, or a gain of 12 or about 11 dB, and the difference is 4 dB. So it certainly makes sense to design these matching networks. You get, a 4 dB improvement in gain as opposed if you don't. So that's certainly worth doing. Right, 3 dB is a factor of 2, so it's more than a factor of 2. Okay, then. So that's the task at hand. Then, just as I mentioned earlier. Go back to it. Looking at this, right? The task at hand is to design this source matching network and this load matching network so that the reflection coefficient looking into the source matching network is the conjugate of that looking into the transistor. And the reflection coefficient looking into the load matching network is the conjugate of that looking into the output of the transistor. Right? So we're going to want gamma S to be S11 conjugate, and we're going to want gamma load to be S22 conjugate, right? where the S11 and S22 are obviously the S parameters of the transistor. Okay, so it's a little different, right, than matching. Matching is some complex load, and we want to end up seeing Z naught here at this pair of terminals. Right, we've done that before. That was an earlier section. This time it's a little different. The load is the characteristic impedance, and we want to put circuit elements in here or stubs, whatever we're going to do, so that the reflection coefficient looking into this pair of terminals is the conjugate of this one. Or another way of saying it is we want an impedance, right, looking into this pair of terminals so that when we take that impedance and subtract Z naught from it and take that impedance and add Z naught to it and take the ratio, we get the conjugate of the reflection coefficient looking into the transistor network. So that's what we're up to here. Okay. And why are we doing that? We're doing that because we want to increase we want to satisfy this unilateral assumption, right? And consequently have the opportunity to increase the gain of the transistor over what it would be if we didn't have those matching networks, would just be the magnitude of S21 squared, right? It's going to be bigger than that. These terms, because of the matching network, these terms right here are larger, both larger than 1, so we're going to get a multiplicative improvement over what we could get if we just used transistor S21. Okay, so that kind of brings us to example 1019, right? Use lumped elements. Right? I need a 2. Design a load matching network and source matching network. Okay, and so, right, I'm going to use lump matching network. Still use stubs, right? So read through his example, his solution to 1019. He shows you how to do it with stubs. I'm going to show you how to do it with lumped elements. Okay, and then in this design, in the stub design that Stu does, he leaves all the distances, stub lengths, and distances from the load in terms of wavelength, stubs in terms of wavelengths and distances in terms of wavelength. He has a follow-on example of that, and he uses, based on that example 1019, and he uses a frequency of 2.4 gigs. So I'm going to use a frequency of 2.4 gig, and I'm going to do it with lumped elements. Okay, so you look at both methods, right? Yeah, good to remember how to do it both ways, both lump matching using circuit elements and stubs. Okay, so right, and what I'm going to do is I'm going to do the source. Let's see, am I doing the load or the source matching? I'm going to do the source matching side, and then for homework, you do the load matching side. Okay, so we'll review that homework when we get through this. Okay, right. So, right, remember, right, here's what we're up to. So, right, the Thevenin equivalent of this, the impedance seen looking back into the source is just Z naught, right? How do you find what that is? Well, you short out the source, and that just puts Z naught across this pair of terminals, right? So Z naught in this case is 50 ohm system. Could be 70 ohm, 75 ohms, some other impedance, but we typically use 50 ohms. And so then I've got this source matching network. I'm going to put elements in this network. And when I want to make sure that when I do that at the operating frequency, the reflection coefficient looking into this network is the conjugate of the transistor's reflection coefficient. Is a conjugate of the reflection coefficient looking in the transistor, right? And so, since in this problem, right, based on the details given in problem 1015, right? 1015 gave us the scattering parameters, so we're going to use, right? We're going to use these scattering parameters in our design right here. So we want looking into here to be the conjugate of S11, and so S11 was 0.56 at an angle of 30 degrees. So we want the conjugate of that, right? So we want it to be 0.56 at an angle of minus 30 degrees, right? You form the conjugate when it's in polar form by just negating the phase. Okay? So looking into here, I got to get this somehow I got to get from the center of the Smith chart, right? We're going to use the Smith chart, obviously, here. I got to get from the center of the Smith chart to some impedance so that when I take that impedance and subtract 50 from it and take that impedance and add 50 to it and take that ratio, I get this 0.56 at an angle of minus 30 degrees, right? So, right, how's this going to unfold, right? So we'll start out uh, using the Smith chart. What's the procedure here? We're going to start out at the origin of the Smith chart and then move around on the Smith chart using, legal moves again, right? You can't get off a constant resistance circle with a L or C. You can't get off a constant G circle with an L or C. Not possible, right? So that's what I mean by using legal moves. And then we need to start at the origin and we need to end up here, 0.56 at an angle of minus 30 degrees, right? So let's take our Smith chart out now and take a look at that. We'll come back to the sheet. So here we go. Let's zoom out. Maybe that'll help a little bit. So here's our Smith chart, right? What do we have here? Well, here is the origin, right? Here's the origin. So what is that? That's 1 plus J0, right? So starting at the load, right? Starting at the load, how do I get to 1 plus J0? I divide 50 by 50, that's 1, right? So that's where I start. And I need to get from here to here somehow, right? I've got to get from here to here somehow using legal moves. Okay. Why do I have to get here? Because this is the 0.56 at an angle of minus 30 degrees spot, right? That's the place where I want to ultimately end up. Right? How do I plot this on the Smith chart? Well, right, this is a reflection coefficient. So I come down and I use this scale and I open my compass out till I get to 0.56, 0.5, 0.52, 4, 6. So that's my radius. Then I draw my circle, which I've darkened so that you can see it when I scan this. It's already scanned and out on the engineering FTP. And then, right, how do I get to this point minus 30 degrees? Well, just read the scale, right? This is 0, minus 10, minus 20, minus 30. So 0.56 at an angle of minus 30 is right there. That's where I want to end up, right? I'm starting here. I want to end up there, right? Well, there's, as usual, right, with stubs and back rotated unity conductance circles, which we've created here. You know how to do that. There's enough experience to know how to rotate this backward. Uh, this is impedance, right? Well, if I end up over here in admittance, that's the same thing as being here in impedance, right? So I can go from 50 ohms to here in impedance, or I can go from 50 ohms to here in admittance, right? Because this point in admittance is the same as that point in impedance. So this point in impedance gives me a 0.56 at an angle of minus 30 degrees. This point, right, which is 0.3 at an angle of 0.3 plus J 2.4, right, will give me an admittance that when I converted it into an impedance would give me this reflection coefficient. Okay. So I can end up here or I can end up here. And I'm going to pick here. Well, that means I have to get to this spot somehow, right? Well, the only way for me to get to this spot, remember, is to slide along a constant admittance, a constant G circle, right? I know this is admittance, so I'm going to speak in terms of G and B, right? If I make an impedance move, I speak in terms of R and X. So get the language right. So I'm going to end up here, right? So, right? So here's my back rotated unity conductance circle. I'm going to call it a conductance circle because I'm going to move an admittance. So I'm going to move from here to here. Right? That's going to be an admittance move. But how do I get to here? Well, I have to get to there from over here, right? You got to work backward. Remember how this works. So that's admittance. This is impedance. So my first move is going to be an impedance move from the origin down to this point. The first move is going to be an impedance move from the origin down this way to this point right here. Then I'm going to flip coordinates to admittance, and then I'm going to go from here to here. So then I'll be at this point in admittance coordinates, which is the same thing as being here in impedance coordinates. Voila, I'm done because being here is 0.56 at an angle of minus 30 degrees looking into that network. Okay, so I told you how to do it. Now let's follow through. Okay. So we want to go from 1 plus J0, right, to start with. And this first move is going to be an impedance move, right, to 1 minus J 1.55. 1 plus J0 to 1 minus J 0.55. Right, so there it is. Right. From 1 plus J0 to 1 minus J 0.55, that's an impedance move. So I'm going to need a series cap, right? I need to go more negative, so I need a series cap, 1 over J omega C. Puts the minus J in the numerator. Okay, so 1 plus J0 to 1 minus J 1.55. I need a minus J 1.55 normalized. So then I multiply it by Z naught to unnormalize it and set that equal to 1 over J omega C. Right? Or I need a C of 1 over 1.55 times omega times Z naught. And so that gives me my first element closest to the load, closest to the 50 ohm load, as a series cap of value 0.86 picofarads, 10 to the minus 12. Puffs. People like to call them puffs. 0.86 puffs. So, right, here's the 50 ohms, and then first element is 0.86 picofarads. Right? What does that do for me? It brings me from the origin to this location right here. Why did I want to get to that location? Well, because when I change from impedance coordinates there to admittance coordinates, I'm going to end up over here. Right? You got to think backward here through the process. So, right, so I've made this move in an impedance move, and I flip across, right, which puts me on the back rotated unity conductance circle at this location. Right. So then I got to move from here down to here. Right. Got to move from here down to here. So that's an admittance move. This was an impedance move. When I flip, that's an admittance move. So I need to go from 0.3 plus J 0.46. You'll note that this point is 0.3 plus J 0.46. Read it off yourself from the notes. And I need to go to 0.3. Note that you can't change the 0.3, right? No amount of J is going to change the real part to 0.3 plus J 0.24, right? So I need some negative. I need to go from 0.46 to 0.24, or I need minus J 0.22 normalized admittance multiplied by the admittance to unnormalized. And so I need a 1 over J omega L, or I need a shunt L to make that move. Right? I solve for L. It's a simple matter to show that it's 15.1 nanohenries. So the cap got me from here to here, flip coordinates. The inductor will get me from here to here. The cap was in series. Why? Because I was in impedance coordinates. The inductor is in shunt. Why? Because I'm in admittance coordinates. You got to keep that stuff straight. Pay attention to what coordinate system you're in, and you'll be okay. Mistakes are made when you so. Am I in admittance or am I in impedance? You got to know that, right? You can't make the proper choice if you don't know what coordinate system you're in. Okay, so this is a series C and shunt L. Series because I'm in impedance coordinates, shunt because I'm in inductance. Shunt because I'm in admittance coordinates. Okay, so then we got our design, right? Pretty cool. Here's our 50 ohm load. We lead off with a 0.86 picofarad capacitor, and then we follow with a shunt 15.1 nanohenry inductor. Okay, so we're it's a little different than matching, right? Before we had some complex load and we wanted to make sure the input impedance was 50 ohms. Not this time. We're starting with a 50 ohm load, and we want to adjust these elements in such a way so as to give us a reflection coefficient that's the conjugate of what you see looking in the transistor where this thing's going to be attached. Right? Transistor is that way, looking to the right of this pair of terminals. So again, we want this. The question is, did we do it right? Right. So we're drawing the circuit and we're checking it using circuit theory. Right. So how are we going to do that? We're going to see if the reflection coefficient here is 0.5 at an angle of minus 30 degrees like it's supposed to be. How are we going to do that? Well, we got to find the input impedance and subtract 50 from it and add 50 to it and take the ratio and see if we get that. Right. So what is Z in here? Well, I just computed the impedances associated with these elements at the 2.4 gig, right? So this one's minus J77, this one's plus J228. And so what is the impedance looking into here? Well, it'll be 50 minus J77 in parallel with J228. So you do the arithmetic. Parallel impedances are, what is that? Is the reciprocal of the sum of the reciprocals. Kind of fun to say. Reciprocal of the sum of the reciprocals. So if you do the reciprocal of the sum of the reciprocals, you get 102.73 minus J82.8, 82.25. So does that give us the desired reflection coefficient? Well, sure enough, Zn minus 50 over Zn plus 50, where you substitute the Zn, gives you 0.56 at an angle of minus 29.03 degrees, are pretty darn close, right? Almost minus 30 degrees. So these two, this series cap followed by this shunt L, gives you an impedance so that the reflection coefficient is the conjugate of what you see looking in the transistor, right? So you got to design, right? We're half done with this problem. The other part of it is going to be your homework assignment, right? You've got to go and design the load matching side, right? The load matching side. So you need to put circuit elements in here so that looking in here, you get an impedance so that that impedance minus Z naught over that impedance plus Z naught is the conjugate of S22, right? Of the transistor. Well, we know what S22 of the transistor is. It is somewhere, right? It's given in here. So it needs to be 0.660 at an angle of minus 120 degrees, conjugate, right? 0.66 at an angle of minus 120. So looking into your load matching network, now you need to verify that after you put your L's and C's, your lumped elements in here, that you get a reflection coefficient here of 0.66 at 120 degrees. Okay, so hopefully you've got enough here to see how to do it. Let's don't bite off too much. There's more in this there's more here that we're going to discuss tomorrow or the next day. Right? There's more material, but hopefully you'll have everything you need. Right? You've got this example, so you're just kind of repeating this, but you're doing it for the load side. I did it for the source side. You're going to do it for the load side. And then I'm using lumped elements. You're going to use lumped elements, but you're going to read the book too and make sure you know how to do it in stubs if you were called upon to do so. All right, pretty good. Slugging away at it, almost through with chapter 10. Yeah. So I'm trying to decide whether to get to the end of 10 and then call it quits, or maybe go in and do a little bit in the EMC chapter. I'm kind of leaning towards doing a little bit in the EMC chapter, chapter 9, uh, but I haven't decided yet. Right? And then we're going to have a final here, take home final pretty soon. Okay, you're going to get an email about all of that once I finally decide how to do it. We're trying to cut down on all the scanning and email and stuff back and forth to each other, but we're going to have to do it on the final. Right? You're going to have to give you the final, put it out on the engineering FTP, give you a certain amount of time to knock it out. So it's essentially a take-home exam, and I want you to do your work independently on that. Right? Don't drive across the state and find somebody to work on it with. You know, as soon as it's posted, you jump in your car and you race across the state. Don't do that. Just sit at your house and work it yourself. Okay. Don't call and ask people about how to do this and how to do that. You do your own work. And then, but you'll have plenty of time to work on it, right? Work through it. It's just going to be like the homework problem. And then scan it and send it back to me, and I'll grade it, and we can wrap this semester up. Hopefully, everyone will do well. I think you will. You should have all the tools necessary to do so. Some of you I haven't heard from, or what happened to you. Hopefully, you don't have the virus and are ill. So hopefully, everyone's well and engaged in this and learning something in spite of the circumstances. Right? A lot of times in life that's required, not because of something, but in spite of something. So work hard and get the job done. I know you've got other classes you're taking and other responsibilities, and it's under perhaps less than ideal circumstances, but again, let's push on and get done. Okay, that's all for today. Turn this thing off.